channel Clinical Biochemistry by Dr. P.K. Prabhakar. Today we are going to talk about nucleosome model. So we will see how nucleosome is going to form and what is the requirement of nucleosome in the cells. So before that one, we have already discussed about the DNA structures, double helical model of DNA, Watson-Crick model for DNA structures, and how DNA is known to be genetic material. So all those things we have already done it. So we'll see what is the requirement of the nucleosome model. So like DNA is double helical structures and it is coiled structures. Roughly in our cells we are having 10 to the power 13 cells. In a human being roughly we are having this much number of cells. And if we will take DNA of one cell of our body, roughly we are having 23 pair of chromosomes, so it means it is 46 chromosome. So if we take 46 chromosome and join each DNA end to end, so roughly we will get 6 feet long DNA in a single cell. If we will combine all the DNA of all the human body cells, it will be, means it is that much big, so it can go from here to sun 300 times. That much big DNA we are having. And all this big DNA, roughly in a single cell we are having 6 feet DNA, and it will be placed in a nucleus. We are having cells, inside cell we are having nucleus. So this 6 feet long DNA has to be placed in the DNA, and in that DNA which we cannot see by naked eye. But so this is a very difficult task to how to place the DNA. So to keep this 6 feet long DNA into the nucleus, we need a better plan or arrangement for the DNA, so that this 6 feet long DNA will be placed in the nucleus. For that one, we are having nucleosome model. So the first nucleosome, in case of nucleosome, we are having double-stranded DNA. This DNA, through different sequence of arrangement, ultimately it is going to form a chromosome. So this chromosome, lastly we are getting after the sequence of arrangement. So first we are having DNA, which already we have seen it. So this DNA whose diameter is 2 nanometer. This 2 nanometer DNA is going to give us roughly 1400 nanometer thick DNA by different forms of arrangement. Through in this sequence of arrangement, one of the intermediate is nucleosome. Other than nucleosome, we are having solenoid structure, we are having chromatin structure. So these are sequential arrangement, and slowly DNA is going to be thicker, and ultimately we are going to get 1400 nanometer base pair long. So first we will see, as you are going to see here. So first we are having a DNA which is of 2 nanometer length, 2 nanometer diameter. This DNA is going to be arranged by nucleosome. Nucleosome, nothing, it is a kind of proteins and DNA wrapped on the proteins. We'll see how it is going to be wrapped. So DNA will be forming the nucleosome model. Nucleosome. On this nucleosome, the diameter will be 6 nanometer. This 6 nanometer diameter nucleosome, it looks like you are having a thread. On that thread you are having a bead-like structure. So it's, you can call it bead on a string. So that nucleosome, this nucleosome is going to be arranged in around a hypothetically axis. So it will be wrapped around the axis. It is called as solenoid structure. So diameter has been increased from DNA, which was 2 nanometer. From DNA it goes to 6 nanometer nucleosome. Then 6 nanometer nucleosome give you solenoid structures whose diameter was 30 nanometer. This 30 nanometer solenoid structure is arranged going to zigzag fibrous structures which is called as chromatin fiber, and its size is 300 nanometer. Its diameter is 300 nanometer. This chromatin fiber ultimately forms a DNA structure, which is normally we are seeing in the DNA during the cell replication during metaphase. So that is called metaphase chromosomes, and diameter for metaphase chromosome is roughly 1400 nanometer. So that is our nucleosome structure, how it is going to be arranged. In this sequential event means we are having DNA to nucleosome. So we had DNA gives us nucleosome gives us solenoid DNA gives us chromatin gives us chromosome. The diameter for DNA was 2 nanometer. Diameter for nucleosome is 6 to 7 nanometer. Diameter for solenoid DNA is 30 nanometer. Diameter for chromatin and DNA is 300 nanometer, and diameter for chromosome is 1400 nanometer. So this is the sequential arrangement. So DNA, which was a double helical structure. This double helical structures gives us a bead-like structure, like we are having. So this is on this one, DNA will be wrapped. So this is like a structure where we are having nucleosomes. So this is bead-like structure. Its diameter is from here to here is 6 nanometer. This nucleosomes, this is going to be arranged around a hypothetically axis. So this is solenoid structure. This solenoid structure gives us a chromatin structure, and chromatin gives us a chromosome. So that is sequential event. In this nucleosome, so nucleosome is one of the important topic, how DNA is going to be arranged, and it is having a significance. So the DNA or nucleosome, DNA normally fills in the chromatin or chromosome is DNA plus protein. This protein is chromosomal protein or DNA protein. This protein normally we are having two types. One is called as histone protein, other one is called as non-histone protein. This non-histone protein and this is histone protein. Normally histone proteins are basic proteins. Basic protein means it is having a basic amino acid, that is arginine, histidine, lysine. Non-histone proteins are normally acidic proteins. Why histone proteins are the basic protein? Because you know that DNA is acid, and normally on acids we are having a negative charge. Basic protein means it is having a positive charge on their cell surface. Our DNA is negatively charged, and if histone will not be basic, histone will be acidic, which will have a negative charge. So negative charge will repel negative charge. So this protein will not bind, never binds with the DNA. That's why we require a basic protein which is having a positive charge. So positive charge of bare proteins binds easily with the negative charge of the DNA. So that's why histone is a basic protein. This is acidic protein because it is having acidic components. Other than this one, there are some functions of other functions is also done by these two proteins. So the most important functions of histone protein is first a structural role. A structural role means histone protein is one of the most important protein which forms nucleosome. So this is the protein which is responsible for nucleosome formations. We are coming there. So first and most important role is a structural role where it forms nucleosome. And second function is the activity. Means every time our DNA is not active for the replication, transcription or translation, DNA will be active only when your cells requires it. So DNA should be active or should not be active, that will be depending on the DNA structures, chromosomes structures. So chromosome will be in the active form or will be the inactive forms, that depends on the histone proteins. Histone will be modified by different kind of reactions. Those reactions are, it will be methylation, acylation, acetylation. These are the chemical reactions which normally modify our histones. So histone will be modified by these three chemical reactions, and because of these chemical reactions, DNA will be active or will not be active. That we will see in the DNA replication process. So DNA activity will be inactive or will be in inactive modes. That depends on the histone's modification status. So it is modified or it is not modified on that one. The major role non-histone proteins. DNA is having number of proteins other than histone proteins. All those proteins which is associated with DNA is called as non-histone proteins. So the function of non-histone proteins are, first, stability of the DNA. Stability. So DNA is going to be stabilized by non-histone protein, like SSB protein. That is going to provide the stability of single-stranded binding protein, single-stranded protein DNA. Second one is, its role is regulatory. Number of DNA involved in the regulatory process, like transcription factor, different components, different kind of factors like initiation factor, elongation factor, termination factor of DNA transcription or translation process. So those regulatory process will be done by those non-histone proteins. And third function is, it is also involved in the enzymatic nature. Enzymatic. So enzymatic like DNA polymerase, RNA polymerase, gyrase, topoisomerase. So those are enzymatic activity. So two broad classes of proteins we are having which is binding with the DNA, histones and non-histones. Histones are basic proteins which is normally having arginine, histidine and lysines. Now in this histone protein is having two important functions. First is structural roles to form nucleosome, and second one is DNA to be active or to not be active. That will be decided by the modification of histones by these three chemical reactions. Non-histone proteins is acidic in nature. It is having three basic major characteristic features. Those characters are, first, it provides the stability of the DNA. Second, it involves in the regulatory steps like transcription, translation, or third, it helps in the DNA as a enzymatic molecules like DNA polymerase and RNA polymerase. Now this histone proteins, because we are going to talk about the nucleosome model, and nucleosome is without histones we cannot do it. So histones normally present only in the eukaryotic cells, because prokaryotic DNA is very small, so they don't need to arrange their DNA in so many forms to arrange it to be in the nucleus. In case of eukaryotic cells, because our DNA is very big, so only we require to arrange our DNA to form in a proper manner so that it will be accommodated into the nucleus. So that's why nucleosome is present only in the eukaryotic cells, not in the prokaryotic cells. And because of this reason, histones is present only in the eukaryotes, not in the prokaryotes. So whatever histones we are having, those histones we are having basically H1, H2A, H2B, H3, H4. These are the 5 important histone proteins. These histone proteins are, H1 is lysine rich. Because all histones are basic proteins, so they will have arginine, histidine and lysines. This H3 and H4 are arginine rich, and these are lysine, serine and lysine rich. Now This out of these 5 histone proteins, these 4 histone proteins, 2 in number. So 4 proteins, 2 in number means 8 proteins. 2H2A, 2H2B, 2H3 and 2H4 is going to form a complex of octamer. So that is called octamer. So we are having a 1 protein, 2 protein, 3 protein, 4 protein, 5 protein, 6, 7 and 1 is behind that one, that we are not seeing it. So this 2H2A, 2H2B, 2H3, 2H4 forms histone octamer. This on this histone octamers, DNA will be wrapped. Like it is going, DNA is going to start from here. So it will be DNA will be wrapped roughly almost 2 times, not exactly 2 times, but it will be almost 2 times. It is DNA is going to wrap down 1.67 times, not completely 2 times. It will be 1.67 times. This DNA is wrapped on that one, nucleosome octamers. Sorry. So how this octamer is going to form? First, H2A combines with H2B, forms a H2A, H2B dimer. This dimer combines 2 in number and forms H2A, H2B tetramer. This is tetramer. Similarly, we are going to form H3 plus H4. It is going to form H3H4 dimer. This dimer going to 2 in number, so it will form H3H4 tetramer. This H3H4 tetramer plus this H2A H2B tetramer combined together and gives you a octamer of 2H2A, 2H2B, 2H3, 2H4. This is how it is going to be arranged. So first H2A H2B combine together and forms a tetramer of that one. Then H3H4 combines together and forms a tetramer, and both tetramers join together and gives you octamer. On this octamer, if you see the structure, DNA will be wrapped on that one. This is nucleosome. So nucleosome will be looks like that one. On the DNA, I have told you DNA will be wrapped roughly 1.67 times. This DNA which is wrapped on the DNA, nucleosome octamer, length is 146 base pair. It is roughly 145 to 147 base pair, but on an average it is 146 base pair. So 146 base pair wrapped on the histone octamer. This histone octamer means once it will be wrapped, it is not completely locked. So wrapping can be wrapped, can be unwrapped. To stop that one, this H1 forms a locking. This is H1, which forms locking, knotting. So it will be almost closed. So if you see the structure, I'll show you the structure here. So if you are seeing here, structure is histone octamer plus 146 base pair is forming this octamer is called a nucleosome core. So nucleosome core of octamer, on that one where 146 base pair is wrapped, that is called basic structure of the nucleosome started. Then slightly further if you go, so this 146 base pair octamer plus H1 and nucleosome octamer When H1 is coming, that's roughly 20 base pair more DNA will be there. So that will be 166 base pair. 146 was the wrapped down the DNA and 20 base pair because of the H1. So 166 base pair plus H1 plus the four things. It is called as chromatosome. This chromatosome, and the difference between the basic structure of nucleosome and chromatosome is the H1 and 20 base pair. Once the DNA between the two nucleosome, if you see the structure of nucleosome, the distance between the two nucleosome, there is a DNA. That DNA length will be roughly 20 to 40 base pair. That is called as linker DNA. So linker DNA is part of both the nucleosome of both the sides. So half of the DNA will be belonging to one nucleosome, half of the DNA belonging to the other nucleosome. So this chromatosome plus 20 to 40 base pair extra of linker DNA and gives you a nucleosome structures. So the sequences will be the basic template of the nucleosome where octamer core is there plus 146 base pair is there. Then we are having chromatosomes where histone octamer, H1 proteins means H1 histones plus 166 base pair, 146 from previous and 20 extra base pair, that is 166 base pair. And the third is nucleosome, that is the final structure where histone octamer is there plus 200 base pairs and H1 histones. So this is the structure of histone. You are seeing there are three nucleosomes are there where octamer is in the center, DNA will be wrapped on that one, and H1 is going to lock, and a small bead-like structure you are seeing in between. Those are non-histone proteins. They are just arranging, they are just stabilizing the DNA. Here you are seeing the sequences of the DNA structure, DNA arrangement. The first is DNA double helical structures. The second one is where diameter you are seeing 10 nanometer. It is nucleosome. Then the third is solenoid structure where bead-like structure is wrapped around a hypothetical axis and its diameter is 30 nanometer. This 30 nanometer solenoid structures gives you a chromatin structures, and chromatin which you are going to say 250 nanometers, and this is going to give you finally DNA of 1400 nanometer. So this is how DNA is arranged in the form of nucleosome to packed into the nucleus. This is the nucleosome models, how DNA will be arranged. Hope you have understand the nucleosome models. If you have any query, you can write in the comment box. If you have not subscribed my channel, please subscribe it.